Hello again. In this video, we're going to use the linearization function L of x that we derived in the last video to help us approximate the change in the y value that occurs on a nonlinear function when its input values are changed. In other words, when there's a change in its x values. Okay, so let me show you how we do this. So suppose we have a nonlinear function which looks like this. And we pick some input value for that function, and we're going to call it a. Now notice when I plug a into the function, I get f of a out, which is right there. Now suppose I pick a different input value called x. When I plug that into the function, I get f of x out, which is right there. So notice that as I make this change in the x value, which we're going to call delta x, we get this change in the y value, we're going to call delta y. And the change in the y value would be the distance from f of x, which is right here, to f of a, which is down here. Okay, so delta y is f of x minus f of a. By the way, delta means a change in, so this is a change in y, right? The change in the y is f of x minus f of a as we make this change in the x value. Now what we're going to attempt to do in this video is to approximate the change in this y value that occurs when we make a change in the x value down here. And the way we're going to do that is we're going to look at the tangent line at this point a comma f of a. Now this goes back to the idea that if the function is differentiable at a point, and you zoom in on that point, and the function is going to begin to look more and more like a straight line. Okay, so in the last video, we showed that we can come up with the equation of this line, which we did in the last video, and that gives us our linearization function L of x. And if you remember, L of x is equal to, from the equation of the tangent line, we got L of x, and L of x turned out to be f evaluated at a plus f prime of a times x minus a. So this is L of x, and we derived that in the last video. That just comes from the equation of this tangent line. Notice L of x, okay, L of x is right here, right? You plug x into the tangent line and you get L of x out. So that's right there. It's approximately the same as f of x, which is right there. Okay, so f of x is approximately L of x, and of course L of x is equal to this. Now if we subtract f of a to the left-hand side, we get f of x minus f of a is approximately f prime evaluated at a times x minus a. Notice that f of x minus f of a is simply the change in the y value, the y. Then x minus a the change in the x value, delta x. And so another way to write this formula is to say that delta y is approximately f prime evaluated at a times delta x. And so this is how we're going to approximate the change in the y value that occurs on the function. It's approximately f prime evaluated at a times delta x. Okay, so just to kind of give you an intuitive sense of what's going on here, f prime of a is the slope of this tangent line. Then delta x is how much we're running. That's our run. So when you multiply the slope of a line by the run, you get the corresponding rise that occurs on the line. Okay, so as we make this change in the x value, delta x here, rise that occurs on the tangent line would be f prime of a times delta x. That's your rise. And that's approximately the same as delta y. Okay, so let me show you an example or two where we use this approximation. Okay, so in this example, we're going to try to approximate the change in the y value for this function when x changes from 1 to 1.05. Okay, and so we're going to use that formula. Delta y is approximately f prime evaluated at a times delta x. That's how we're going to approximate the change in the y value. Okay, so we need f prime evaluated at a. First of all, a is equal to 1 here. And the change in x would be the difference between these two x values, so that's 0.05. Okay, and now we need f prime, then we're going to evaluate that at a. So f prime of x, all right, so just the derivative of this function would be 9x to the 8th minus 2. And then we're going to evaluate that at a, at 1, because a is 1 here. And when you plug that in, you get 9 minus 2, which is 7. Okay, so that's the slope of the tangent line to this function right at a is equal to 1. Okay, and so you're going to multiply that slope, the slope of that tangent line, by the run. The run in this case is 0.05. And this is going to give you the rise that occurs on the tangent line as you make this run. And that's approximately the same as the change in the y value that occurs on this function as you go from x equals 1 to x equals 1.05. Okay, so in this case, it looks like you get 0.35. Now, the actual change in the y value would actually be f evaluated at 1.05 minus f evaluated at 1. Okay, that's the actual change in the y value that occurs on this function. And our approximation for that using this formula is 0.35. Now, I just want to show you how good of an approximation this is. So if you go to your calculator, if you have a TI-84 calculator, one quick way of doing this is go to your y equals button, enter in the function, so x to the 9th minus 2x plus 1. And then you can go to calculate the value when x is 1.05. Okay? And so the y value that comes out is, that 0.45132. Let's write that down. Okay, and then we're going to find, and let me just put in 822 as well, the last 3 digits, just to be as accurate as possible. Okay, and then we're going to evaluate the function when x is 1. So go back to calculate the value when x is 1. And of course you get 0. You can do that without the calculator. Just plug a 1 in here. And so you get minus 0. So this is actually the change in the y value. That's delta y. And we're approximating it as being about 0.35. Okay, so then let me show you one other example where this approximation method comes in handy. So what we're going to do is we're going to approximate the change in the surface area of a spherical hot air balloon when the radius decreases from 4 meters to 3.9 meters. So imagine you have this hot air balloon, right? Initially starts with a radius of 4 meters, and it has a certain surface area to it when the radius is 4 meters. But then the radius decreases to 3.9 meters, and of course, as that happens, the surface area of the hot air balloon is going to be smaller. And what we're going to attempt to do here is approximate the change in the surface area that occurs when the radius decreases from 4 to 3.9 meters. Okay, so here's how we're going to do it. The change in the surface area, right, this is the exact change in the surface area, is approximately the derivative of this function, evaluated at a, times the change in the x value. The only difference here is I'm calling this delta s instead of delta y, since this is output is s instead of y here. Oh, and I should do that with the r. The input value, the input variable is called r here, so it's a change in the radius, a change in the x value. Okay, so a is 4, because that's where we start off at. It's our beginning radius. And then the change in the radius would be negative 0.1. Now it's negative because it's decreasing. So that's our delta r. Okay, now let's find s prime of r, in other words, the derivative of the surface area formula. So the 4 pi is just a constant, so when you take the derivative of this, you get 2r times that constant. And that gives you 8 pi times r. Okay, now we have to evaluate this at a, and here a is equal to 4. So we get 8 pi times 4, and that gives us 32 pi. Okay, then we multiply that by the change in r, which is negative 0.1. Okay, and so let's just plug this into the calculator and see what we get. Okay, so 32 times pi. Pi is somewhere on here, right here. It's this blue button, times negative 0.1. Okay, so it's about negative 10.05. I'm just going to round that off. Okay, and this is in square meters. Now, that's our approximation for the change in the surface area. The exact change in the surface area, right, delta S, would actually be the surface area at 3.9. Of course, to find the surface area when the radius is 3.9, you would plug a 3.9 in to this formula. So this is going to give us the surface area when the radius is 3.9 minus the surface area when the radius is 4. So I'm going to plug a 4 into here. Okay, so let's figure out what that is and compare the two. Okay, so we get 4 times pi times 3.9 squared minus 16 pi. I forgot to square this 4, okay? That looked way off, and it is. This is squared, right? So there was something wrong there for sure. So let me go back. So it's 4 pi times 3.9 squared. So 4 pi times 3.9 squared minus, okay, so this is going to be 64 pi, because this is 16, 16 times 4 is 64, so minus 64 pi. Okay, and so that's the exact change in the surface area. It's like negative 9.93 if you round it off. Okay, so that's a pretty good approximation. Okay. So again, this is the exact change in the surface area that occurs, and this is the linearization approximation, the change in the surface area. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.